So we've now seen an example of the structure of a feed-forward neural network that we can use for binary classification, but we haven't actually spoken about exactly how you figure out what the parameters inside the neural network should be. How do you actually train this thing? And so in this video, we're going to look at the backpropagation algorithm. This is really the fundamental building block of neural networks, and we're specifically going to apply it to our little binary classification feed-forward neural network. I'll start by doing that, and then I will show you in general what the backpropagation algorithm looks like. So we're going to do binary classification with a feed-forward neural network, and the question is, how do we fit the parameters of our binary classification model? And as usual, as we did in binary logistic regression as well, we're going to use gradient descent to minimize some loss function, and specifically we're going to use the negative log likelihood. Now for this example, I'm going to basically make a very small, well, it's maybe a big simplifying assumption, which is that we only have a single training item xn, yn that we're going to fit the model to. If you have more samples and you use the negative log likelihood, then you can basically just take the sum over all of those samples individually. So you can very easily, if you just step through the math again, extend this kind of arbitrary case to the case where we have more training examples, a whole batch of training examples maybe. And we're going to stick with this binary classification model. So just as a reminder, we're basically saying that we've got some model F, okay? And we can maybe denote this as y hat n is equal to this. And if we do that, then y hat n for our model takes on a value between 0 and 1. Now, if you've gone through the logistic regression video, then this loss function here would look familiar. If you haven't, it looks kind of scary, but it's not that tricky. So definitely go and look through the logistic regression videos. Let's quickly jump back and just see what our model actually looks like. So for this example, our model looks like this. We're going to do a binary classification with a feed-forward neural network, and now we're going to learn our hidden representations here. You can also represent it in vector form like this, and this makes it quite convenient because now we can really see what are all the parameters that we're going to have to set with our negative log likelihood loss function. So all the parameters are, we've got a W1 matrix here, we've got the bias vector here for the first hidden layer, and then for the output we've got this W2 vector, and then this bias 2 scalar that we need to fit. So just to summarize, we've got all these parameters theta, and we need to fit all of them. And how are we going to fit it? We're going to use gradient descent. And to do gradient descent, that means that we need to get the partial derivative of the loss with respect to every one of these elements. Now you could go about this in kind of a more ad hoc way, where you look at that graph and you try and manually write down the loss function with respect to, let's say W2. Okay, you can do that. And you can go and try and figure out that. And if you can, that's great, because then you can immediately do gradient descent on W2. But what the backpropagation algorithm gives us is a principled procedure to obtain these gradients, these derivatives that we need for gradient descent. Basically what it ends up being is that we're going to apply the chain rule of differentiation. We're going to apply that while reusing results that we've already computed. So I'm going to go straight in and actually show you what the backpropagation algorithm looks like. I represent it like this. So it's basically a 4-bullet process, which is quite easy. So what you do is you start by representing your neural network as a computational graph, and I will explain in a second what that means. Then what you do is, in your graph, you make a forward pass, which is you start at the input of the graph, calculate the outputs of each of the operations in the graph, and you store these values. Then you take a backward pass, which is where you start at the output of the graph and move backwards. And for each of the operations, in your graph, you determine and calculate the derivative of the output with respect to each of the input variables to that operation. Okay, so this probably doesn't make any sense because we need to look at an example for it to really make sense. But what we'll see in a second is that we will have this computational graph, and what I do is operations are denoted with little blocks, and then the inputs and the outputs to those operations are denoted along the edges. And what this step says is that if I have an operation like this one, then calculate the derivative of the output with respect to each of the input variables to that operation. So if this is one block in my neural network, then what I will do is I will calculate the derivative of the output with respect to one of the inputs, which is like V in this case. This is one of the inputs to the block. And then the other one is U, so I will also calculate dz partial derivative with respect to U. This will all become clear in a second. And then for each of the input variables to that operation, so for V and for U, and if there's some others like W1 or a B, for each of them, what we do is we set this thing which is called the accumulator or the error signal, we set that equal to this. And what is this? This is just a partial derivative of J with respect to that variable. Now, unfortunately, we won't know this, but if we know the chain rule for vector calculus, then you can decompose this thing as dz du times the partial derivative of the loss with respect to z. If I wiggle u, what is the effect on my loss function right at the end, right? So there's maybe a big chunk of neural network here, and then right at the end we've got a little loss that comes out j. And gradient descent, ultimately what we want to do is we want to figure out if I wiggle u, what is the effect on the loss? And if I know that, then I know in which direction to change u in order to make the loss lower. And what this step does is it says, listen, if I want to know what the effect is of u on j, then all I need to do is I need to look at what's the effect of u on z, okay? And then multiply that with the effect of z on j. Okay, so basically the chain rule, if I wiggle u, z will get wiggled, and if z wiggles, then j will change. And that's how I figure out how to wiggle u in order to make j lower, okay, at a very high level. Okay, final step, we then use the calculated derivatives to take the gradient step using gradient descent, and then we go back to the forward pass with the new set of parameters. After updating our parameters with gradient descent, we make another forward pass, and we then calculate the derivatives at that specific new point and re-update our error signals or our accumulators, then repeat again, and you go back again and again. Okay, and you will see in a second why this actually works and what this gives us. So let's just jump back and see where we're at and what example we're doing. So we're looking at binary classification with a neural network. Okay, and our neural network, if we look at the diagram here at the bottom, it takes some input x and then we get some output y hat. Okay, and what we do in our neural network is to get our loss function j, what we do is we compare y hat, the prediction from our model, to the actual label y that was assigned to this input x. Okay. So this is the vector diagram. You've seen the kind of neuron diagram before as well. Now let's see what the computational graph for this thing looks like. So I've been hinting at this computational graph, but let's now really see what that looks like. So first viewing, it looks a little bit crazy, but it's actually just those steps in that vector diagram expanded kind of systematically. So each of the blocks in our computational diagram represents one operation. Now you can go and look again at that vector diagram from before, but you will see that what we have is we've got our input x, and then what we do is we calculate like a z1, which is a linear transformation of x, okay, which is that weight matrix times x plus the b vector, and that gives us this z1 output. And then we push that through some nonlinearity, which might be like a ReLU or a sigmoid. Okay, and that gives us the activations, in this case of our first hidden layer. And in the binary classification case, we have a single output layer. And what that output layer does is it just takes the activations from the previous layer. We take those activations, we take the dot product with a weight vector, and we add a bias scalar. And maybe we have a sigmoid here in order to get things to be between 0 and 1. So this is the predicted output of our model for this input X. And then we compare this predicted output to the ground truth output that was actually assigned. So you can actually say here that there's another input here, which is Y, the real output that was assigned. And if I have my prediction and I have my Y, then I can calculate the loss. Okay, so let's go through the backpropagation algorithm. The forward pass says basically calculate the output of each of my operation blocks by basically going from the input to the output side. Now that's really easy. If I've got my input xn, my single training item, then I just basically go through and I calculate all of the outputs. So it's important to emphasize we start with a random guess for all of our parameters. So we start with some guess for B and W, B and W. For our parameters. So given that initial guess, I feed in xn here, I calculate z1, I calculate a1, I calculate z2, I calculate y hat, I compare y hat to y, and I get my loss value. Excellent. Forward pass, really easy. Let's quickly recap the backward pass. What we will do is we will determine and then calculate the derivative of the output variable with respect to each of the input variables, to each of the operations, each of the nodes in my graph. Okay, so that's the first step. And then what we will do is we will set the accumulator for each of the inputs u. We will set that equal to this. This will become clear in a second. So let's just go through those operations. So what happens is we start at the output of our model, and we're going to go backwards through the model. I guess that's what the backprop says. So let's start at this. I'm just going to denote this as A. We look at this operation A here. So A. Determine and calculate the derivative of the output with respect to each of the input variables. Okay. Now this operation has a y hat and a y as the input variables. You'll see in a second you don't need to calculate the derivative of the y variable, but we do need the partial derivative of the loss with respect to y hat. Dunk, dunk, dunk. Okay. And you can go through these steps. The partial derivatives of the log, it just goes 1 over y hat. And here we've got a minus, and the minus pops out, so that minus and that minus becomes a plus. Okay, so that's the kind of this step in the backward one. And then what we do is for the input variable, y hat, we're going to set that equal to this. And because we're at the output, this is actually quite easy because it's just exactly this equation. So the accumulator or the error signal for y hat is just equal to the partial derivative of this. Now, it is useful to just be a little bit explicit here, right? What is y and what is y hat, okay? Where did we get these values from? Now, these are the values. Y obviously is the ground truth label, whether this is a 1 or a 0. And y hat are the values that we got in our forward pass, okay? So in our forward pass, we went through this whole thing at our specific guess of B and W and all the other, and this B and W. At that specific guess, we got a specific prediction for y hat. And of course, it's also dependent on the specific training example, right? So if we had a different training example, then y hat would be different, okay? So to just kind of denote that, I'll just write here that we're calculating the partial derivative of j with respect to y hat, where at this specific point of x is equal to xn, y is equal to yn, okay? And then at that specific point, we're calculating the partial derivatives. I should also say this bar also includes the settings of all the other parameters at this specific point. And the point I'm trying to make here is that this thing here is actually, it takes on a numerical value, right? It's actually a numerical value that we can use, okay? So then this is actual numerical value. So we're now looking at B. So this is B. So this is this operation here. Again, what we do is we calculate partial derivative of the output with respect to all of the inputs, okay? And in this case, there's only one input, and this is Z2. What we will end up doing here is, this is quite simple. So Z2 Y hat is just equal to G of Z2. Okay, so the partial derivative of this case would just be the derivative of G, whatever G is. Okay, in this case it might be a sigmoid, and if it is a sigmoid, that's nice because you can just go and look up on Wikipedia what is the partial derivative of a sigmoid with respect to its input. So this equation will be general, but now we need to get the specific numerical value for this for Z2, our error signal for Z2, and this is equal to partial derivative of J with respect to Z2, this thing we calculated here already. If I wiggle Z, what is the effect on my loss J? Okay, how can I get this? Well, I just use the chain rule. So I know that what I can do here is I can take the partial derivative of Y with respect to Z2, and I can multiply that with the partial derivative of J with respect to Y hat. That's just this chain rule, and this is just the chain rule for scalar values. What is this? What is this? I know it. It's this value here. What is this? I know this. I calculated it before. So that's really, really convenient. So I can then write this out as just saying that this is just equal to G of Z2 dash, because it's the derivative, times the error signal from Y. Okay, let's just look at this again. So remember, what we're trying to do is we're trying to figure out how should I wiggle Z in order to make J lower. Okay, and if I wiggle Z, then I will wiggle Y hat, and Y hat will influence J, and that's what this equation basically says. Okay, now the backprop algorithm, what that tells us is that we need to calculate the partial derivative of the output with respect to each of the inputs, so W2, B2, and A1. Let's look at W2, because that's the interesting one. So we need to get the partial derivative of Z2 with respect to W2. Okay? Ooh, okay, now this looks a little bit crazy because now there's vectors and matrices here. Well, actually just vectors. But if you've gone through the vector and matrix calculus video, then this isn't actually so hard. And you can go and look this up on Wikipedia, or you can follow along with the matrix and vector calculus video. But you will see that it looks a little bit like the scalar case. So the partial derivatives with respect to B, that would just be equal to 0. And the partial derivatives with respect to that thing, it will turn out that would just be the A vector of our first hidden layer. Okay, cool. So now we need to update our error. And I'm just going to drop this bar symbol here now because you know it's the error at this specific point in time where we have settings and guesses for all our parameters, and we're looking at this specific training example. Okay, so now the error for W2, you can see that I put a little line here because this will now be a vector. Why is it a vector? Because this thing is equal to the effect when I wiggle W2 on the loss J. And that is a vector, if you followed along through the vector and matrix calculus videos. Okay, so how do we get this? Well, we apply the chain rule for vectors. So I do the partial derivative of Z2 with respect to W2 times, and then the effect of Z2 on my loss. So the point here is if I wiggle W2, then I will wiggle Z2, and Z2 will then influence J. And I can summarize that in the chain rule like this. And the very nice thing is, what is this? It's just A1. So I've got that. Awesome. What is this? I got it in the step before. So I've got that as well. And I've got a numerical value for that. And I then have my error signal for W2. Amazing. Okay. Okay. So just pay attention here. What we have here is we now have the derivative, the partial derivatives of W2, this vector here with respect to the loss. So what do I need to do to W2 to make the loss go down? I just do gradient descent using these partial derivatives. And that will make my loss actually go down. So if I do gradient descent on W2 using these partial derivatives, then I have a method to go down with J. Now it looked very complicated, but the point here is you have a general method that tells you how to get to the partial derivatives, and instead of having to look through this whole graph, you only need to look at the output of that node with respect to the input, okay? And because you have this partial derivative, this thing already, you don't have to look any further. Okay, now it looks simple here, but we're going to go further down here and you will see that this principle stays that way, that you basically calculating these partial derivatives by using stuff that you've already calculated before, so you don't have to do some very complicated chain rules through this graph in an arbitrary way. So I'm not going to go through all of them, but the error signal for B2, and in this case, again, for B2, we've got this, we can calculate that, we've got that, and so we're all happy on the inside. And then we also do this for A1, the activation one. This isn't a parameter that we want to update, but it is an error signal that we're going to need in order to update these parameters. This is equal to Z2 with respect to A1. Now this is a vector, right? You need to think through this carefully. So that's a vector of partial derivatives, but I can get that using my vector and matrix calculus identities. And I've got this, so I can calculate a numerical value for A1 as well. So I'm going to skip D because it's very similar to block B here, a very, very simple one. And then I'm just going to jump to E, and for E I'm just going to look at W1 because this is the biggie. Okay, so let's look at that block E here. What we want from block E is we want to know what is the error signal with respect to matrix 1. Okay, this weight matrix 1. Now we know that this is the partial derivative of J with respect to the matrix. And if you've watched the matrix and vector calculus videos, then you will know that this thing is a matrix where you've stacked all the partial derivatives in that matrix. What you wouldn't know is how to use the chain rule in this case, because I didn't actually explain the chain rule with matrices and vectors. But let's just, I'm going to put this in quotes because it's not actually true. Let me put it in green maybe. So if we did have the chain rule, then it maybe would look something like dz1, the output, which is a vector, with respect to weight 1, times dj of dz1. Now the reason I put this all in quotes is because, and this is why it's so important to look at these things carefully. What the fudge is this? Here I've got a vector with respect to a matrix, okay? And I don't really want to go into the details here of what this is. I've got a longer note so you can look through that. But you could maybe guess what this will end up looking like. So let's just look at this. So here we've got Z1, W1. What do you think? What shape will the partial derivative of, I'll put this in quotes again. What do you think the Z1, if you had to guess, and I'm waving my hands because this, I haven't actually defined this formally. What do you think this will look like? If you just think of this as scalars, then you will probably guess something involving x, and you will actually not be wrong. Okay, so, and now I'm putting this in black again because this is actually the truth. It turns out that this is the error signal of Z1, that is the same as that, times X transpose, which kind of looks like that. Okay, now I've waved my hands here because the problem here is basically I haven't defined a chain rule with matrices, and I would actually encourage you to read through my note called Yet Another Introduction to Backpropagation, where I really go through the steps to define and to motivate that this is really the answer. But it looks kind of like this, and I think maybe if you squint at it enough, then you will be happy and satisfied that this answers the question. One little hack, if you wanted to do this for some other graphs is that you can look at the shapes. So you will be able to figure out what this thing's shape looks like. You will know what this thing's shape is, and then you can kind of guess that it's X, and then you would realize that you need to flip the two and take the transpose in order to get the right shapes out. If you want more details on this, please go and read the Yet Another Introduction to Backpropagation note. Okay, let's just do one more variable at this final operation. So operation E, let's just look at the error signal, the accumulator for B1, which is a vector. So this thing is a vector. So the partial derivatives are all vectors as well. This one is easier than the W1 one because all we need to get is the partial derivative of the output Z1 with respect to B1. And then this times dj dz1, which is just the error signal of z1, which is also a vector. Okay, and you've got, this you can get, so you've got a numerical value for B1. Intense, okay, it looks quite scary, but what you actually have done here is you've got a generic way in order to get the partial derivatives for any of your parameters with respect to the output, J. So why does this work? And maybe I don't have to spend too long on it because you can already see that it's just a systematic application of the chain rule. So let's take this last one, this error signal for B1 thing, and just see this one line looks quite simple, but if you go through all the steps, what you're actually doing is you're composing a whole bunch of these chain rules. So let's just write that out explicitly. Okay, that's just what we had before. But then this thing, so what happens if I wiggle Z1? Well, I can write that in terms of the partial derivative of A1 with respect to Z1 times dj dA1. Okay, so I can expand this. Now, what's this? Go back. What happens if I wiggle A? I wiggle Z2. Z2 has an influence on J. Okay, and you can continue in this way. So let me just jump the gun. But all that this is just the chain rule being applied again and again and again. Okay. And so what backprop really is a procedure for getting the partial derivatives. And what does the procedure really do? Recursively applies the chain rule. Okay, but we don't have to calculate all of these things separately, because if I've calculated this once, then I can use it in all the places where I need it, right? If I've calculated the partial derivative, this error signal of Z1 before, then I don't have to calculate it again and again and again. So I hope that makes sense. The one last comment that I wanted to make is something I've probably said a few times already, which was, why did I use this kind of bar notation here at this point? And the point that I want to make here is just that all of these matrices and vectors that we get out here are actual numerical values at a specific setting, right? So we guess a setting for B1, W1, B2, W2, and we've got some specific training data that we're feeding through, in this case just one training example, and for that training data and for that guess of parameters, then we're going to get the partial derivatives at that setting, at that point. Okay, and that gives us numerical values. I could have maybe written that first one as dj dy hat, where at the specific training item, or my batch of the data that I'm feeding through, at the specific output y, and at this specific setting of my parameters. So my parameters, the w's and the b's and all of them, are set to my first guess, okay, which I denote as phi hat m, okay. Now, after I've made my pass, now I actually update all my parameters. Okay, so let's just recap. Forward pass, get everything. Backward pass, get all my partial derivatives. And now I actually take a gradient step. So I change B1, I change W2. And how do I change W2? Well, I use the gradient that I already got here. Okay, so I'm actually updating it. Okay, so maybe I could write that my new guess for my parameter at iteration m plus 1, that is just the old guess, m, and this is the guess at which I actually calculated the actual numerical values for my partial derivatives. Okay, minus, and this is just the gradient descent equation, dj d theta, where at the specific old theta that I was looking at. Okay, so this is just the normal gradient descent equation. But I just wanted to make clear that you guess these values, you make a forward pass, you make a backward pass, you update the parameters. Now you've got new guesses for your parameters, forward pass, backward pass, update again, and you cycle through. And in the next video, I will actually explain that I did this for the specific case of binary classification with a neural network. But this procedure you can apply to any computational graph. So I can make this thing way more complicated and still apply the same procedure. And that still allows me to get my gradients and thereby do gradient descent. So what happens when we apply this model to the binary classification task that we kind of started with, then you end up with a decision boundary looking like this, which accurately classifies iris versicolors versus not iris versicolor flowers. You can also plot the kind of the probability. So red is close to 1 and blue is close to 0. And you can see that at the decision boundaries, there's kind of like uncertainty. And here we've got uncertainty. Here we're very certain that this is an iris versicolor.